So let me ask you something. Do you ever feel like you are just, I don't know, completely drowning in raw data?
Oh, constantly.
Right. Like we have this collective delusion right now that if you want to deal with information overload or if you want to build a smarter AI or even just be a smarter human, the secret is a bigger bucket.
Exactly. Just pour more in.
Yeah, we try to read like 3 books a week, or we scrape more data, we build larger databases, we just hoard it all. But what if that entirely misses the point? What if true intelligence isn't actually about how much raw data you hold, but about how efficiently you compress it?
It's a huge paradigm shift. It fundamentally flips how we approach learning and, well, system design in general.
Hmm.
Because we tend to equate intelligence with volume, right? Probably just because volume is really easy to measure.
Yeah, it's easy to say, oh, my database has 10 million rows.
Exactly. But when you look closely at how expertise actually functions, whether you're talking about biological minds or silicon ones, volume is really just a byproduct. The real engine of intelligence is structure.
Okay, structure.
Yeah, it's the ability to just ruthlessly discard the noise and retain only the load-bearing elements of a concept.
Which brings us to the mission for this deep dive. Today, we are looking at a really fascinating state-of-the-art generative AI research paper. It's from Second Brain AI Labs, and it's called Atomic Units of X, the compression layer of intelligence.
It is such a great paper.
It really is, and the goal here is to decode this framework because it attempts to solve a massive problem in current AI architecture while also kind of holding up a mirror to how our own brains work. So, okay, let's unpack this. To set the baseline, we need to talk about where current large language models are, well, dropping the ball. The paper calls it the representational gap.
Right, so contemporary LLMs are undeniably amazing, obviously, but they have this structural blind spot in how they represent knowledge. They basically operate at two extreme ends of a spectrum, and they completely miss the middle.
Meaning what, exactly?
Well, on the micro level, they process individual tokens, which, are essentially just fragments of words.
Right, tiny little pieces.
Yeah. And then on the macro level, thanks to systems like RAG, retrieval augmented generation, they pull in these massive chunks of text, sometimes entire documents.
So it's kind of like a person trying to learn biology by either, I don't know, staring at a single cell through an electron microscope, or trying to swallow an entire medical encyclopedia in one gulp.
That is a perfect analogy. Because the problem with the microscope approach is that a single token is just far too small to hold a stable, actionable concept. Like the word fragment revol, R-E-V-O-L, doesn't mean anything on its own until it becomes revolution or revolving.
Yeah, it's just raw letters.
Right. And conversely, the encyclopedia approach is just way too messy. A full document might contain 50 different concepts, but they're all buried under, conversational filler, weird formatting, and irrelevant tangents.
So it forces the AI to constantly sift through all this garbage just to find the actual point. But the thing is, human beings don't learn this way. We don't just process raw letters one by one, and we certainly don't memorize entire books verbatim. If humans don't learn this way, how do we actually do it?
Well, we rely on a cognitive process called chunking. And the researchers argue that to understand how AI should work, we first have to look at cognitive science. Human experts bypass the severe limitations of working memory by basically compressing raw data into meaningful chunks.
Oh, like the classic chess studies, right?
Yes, the Chase and Simon chess studies from the 1970s. This is the foundational proof of chunking.
Right, so this is where they took a master and a novice, right? They put a complex board position in front of a chess grandmaster and a beginner, let them look at it for just a few seconds, and then asked them to recreate it from memory.
Exactly. And the masters could recreate the board almost perfectly, whereas the novices completely failed. They could barely remember a few pieces.
Because, what, they just have photographic memories?
Well, that's what people assumed for a long time. They just thought chess masters had superhuman memories. But then the researchers added a twist. They took the chess pieces and placed them randomly on the board.
Like in configurations that broke the rules.
Right. Total nonsense setups that would never happen in a real game.
And what happened?
The master's memory advantage completely vanished. They performed no better than the novices.
Oh, wow. Wait, really?
Yeah, because the masters were never actually memorizing the individual coordinates of 32 isolated pieces. They were seeing chunks. They'd look at the board and see an Alekine's gun or a kingside castle. They saw zones of control and pawn structures.
Ah, I see.
So when you randomize the board, you completely destroy the underlying logic of those structures. Suddenly, the masters were forced to look at the board piece by piece token by token.
They were forced back to the microscope.
Exactly, they lost their chunks. The masters had successfully compressed the surface-level complexity of the board into higher-level atomic units. And we actually see this in every high-level profession.
Like what? Give me another example.
Take emergency medicine. A novice medical student looks at a patient and just sees a terrifying, disconnected list of data points. The patient has crushing chest pain, they're sweating profusely, a specific blood enzyme called troponin is elevated,
Right.
and the ECG monitor shows this strange squiggle known as ST elevation.
Which is just an overwhelming amount of raw data to juggle while a person's life is literally on the line.
But an attending physician doesn't see those as isolated data points.
Huh.
Their brain instantly compresses all of that raw surface data into a single diagnostic atom, a STEMI.
The STEMI.
Yeah, STEMI.
Yeah.
It's a specific severe type of heart attack. And that one atom instantly dictates an entire flowchart of downstream actions. It means calling the cath lab, administering heparin, prepping for surgery.
Okay, I'm looking at the STEMI example, and I'm struggling to wrap my head around how this isn't just like data compression in the traditional sense. Wait, so is an atomic unit just a fancy word for an abbreviation?
No, and that is a crucial distinction. Think about it. A standard zipped file on your computer is useless until you unzip it, right?
Right, you have to decompress it back into its massive state to actually read it.
Exactly. And an abbreviation or an acronym, sure, it might save ink on a page, but it doesn't do any functional work. An atomic unit, however, preserves operational meaning in its compressed state. The paper uses the evolution of mathematical notation to illustrate this, actually.
Oh, okay. Walk us through that.
So think about the written English phrase 1 plus 1. You could abbreviate that to the letter O to save space, right?
Sure.
But the letter O doesn't help you perform mathematics. However, if you compress the phrase into the symbols 1, the plus sign, and 1 plus 1, you haven't just made the representation shorter, you have preserved the operation itself.
Ah, because 1 plus 1 is a functional building block. It's not just shorter than spelling out the words. It allows you to move into algebra later. It's reusable and it's composable.
Composable is the absolute key word here. You can take 1 plus 1 and combine it with other mathematical atoms to build complex equations. Then you compose those equations to invent calculus. An atomic unit isn't just a passive label, it's a structural primitive that you can actively build with.
Which perfectly sets up the mathematical framework of the paper. Because now that we know what an atomic unit is, how do we actually measure its power? The researchers introduced something called the compression calculus to quantify this.
Right. If we are moving from raw surface data to atomic units, we need to quantify the leverage we are gaining. So they establish a baseline metric called the atomic compression ratio.
And that measures what exactly?
It measures the length of the raw surface representation. So like the sprawling list of a patient's symptoms against the length of the atomic representation, which would be the single diagnosis.
Okay, so if your atomic version is 10 times shorter but preserves all the actionable meaning, your ratio is 10.
Exactly. That makes sense as a baseline.
Right.
But then they introduce compositional compression gain, which measures the efficiency gained when these atoms start combining. And this leads to what they call the compounding cascade.
Compounding cascade. This was the most mind-bending concept in the whole paper for me.
Yeah, it's wild. The thesis states that compression across abstraction layers is multiplicative, not additive.
Right. So when you stack layers of valid abstraction, you don't just add the efficiency savings together, you multiply them. I want to break down the specific math they use in the paper for this because it scales incredibly fast.
It really does.
So they pose a hypothetical system with 7 layers of abstraction. Let's say each layer only achieves a very modest 5x compression over the layer immediately beneath it.
Okay, a 5x compression.
Yeah, so layer 1 compresses the raw data by a factor of 5, layer 2 compresses layer 1 by a factor of 5, and so on. Now, if this system were merely additive, your total compression over 7 layers would just be 35x.
But due to the multiplicative nature of the cascade, it is 5 to the power of 7.
Which equals 78,125. By the time you reach the 7th layer, your atomic representation is nearly 80,000 times more efficient than the raw surface data it was built upon.
Yeah, it's staggering. Here's where it gets really interesting. It is essentially an abstraction dividend.
Like compound interest in finance.
Exactly like compound interest. Every time a domain invents a new, valid layer of abstraction, like computer science moving from binary cum to assembly language to C++4 to high-level frameworks like React-to-Go, it multiplies the value and efficiency of everything beneath it.
That's incredible.
This compounding effect is literally the only reason human software architecture can scale to millions of lines of code without just collapsing under its own weight.
But the researchers do include a mathematical reality check here, right? Because they introduce a theorem called bounded amortized compression, meaning this cascade isn't infinite magic.
If we connect this to the bigger picture, yeah, you can't just keep compressing forever. The compression is strictly constrained by the actual informational entropy of the specific domain you are working in.
Let's define that for a second. Because usually when people hear entropy, they think of thermodynamics, like chaos and disorder in the universe. How are we applying it to data here?
Well, in information theory, entropy refers to the level of inherent unpredictability in a system. So if a system is purely random, it has high entropy. There are no underlying rules or recurring patterns to extract. You cannot compress randomness.
So if I flip a coin 1,000 times, I can't compress that data into a neat little atomic unit because there's no logical pattern dictating the sequence of heads and tails.
Precisely. But domains like the tax code or Python programming or clinical diagnostics, they have incredibly low entropy. They are highly structured systems built on repeating logical rules and predictable causal chains. The compounding cascade relies entirely on the presence of those deep, recurring regularities in the real world.
Which introduces a massive trap for anyone designing these AI systems. Because think about it, if compression is this powerful and higher abstraction layers give us 80,000x leverage, why don't we just compress everything into a single massive atom?
Right, like why not just build one atom that represents corporate contract law?
Exactly. Just one giant atom for everything.
Well, the paper identifies two fatal traps of system design: granularity and quality. Finding the sweet spot is the search for the Goldilocks zone. Atoms cannot be too small, and they definitely cannot be too large.
The granularity trade-off makes intuitive sense when you look at software code.
Yeah, if your foundational atoms are too small, the cost of composing them completely overwhelms the system. Imagine a software code base made up of 10,000 tiny functions, where each function is literally only one line of code.
Yikes.
Right. Yes, your individual atoms are highly compressed, but the computational overhead required to just find the right function, parse it, load it into memory, and then orchestrate 100 of them just to execute one simple task. It makes the system unmaintainable.
It's like trying to build a skyscraper, but your only building materials are individual grains of sand.
That's a great way to put it.
The atoms are too small to be structural. You end up spending all your energy just trying to glue the sand together.
Exactly. But swinging the pendulum the other way is just as destructive. If your atoms are too large, they lose all their reusability. Imagine a lawyer trying to treat an entire 150-page commercial lease agreement as a single, indivisible atom.
I mean, it perfectly compresses that one highly specific real estate deal.
Sure, but it is totally useless for any other client because the details are too rigid. You can't reuse it.
So the optimal granularity is finding those mid-level structural primitives. For a lawyer, that would be like clause-level atoms. An indemnification atom, a force majeure atom, a termination for cause atom.
Exactly. They are small enough to be universally reusable across different contracts, but large enough to actually save you time when you snap them together.
Okay, so once you nail the granularity, you face the second trap, which the researchers call the quality imperative. And this is basically the dark side of the compounding cascade.
It is. Because we established that compression cascades multiplicatively. The danger is that errors cascade multiplicatively as well.
Oh, wow.
Yeah. The paper introduces an atomic quality multiplier to prove that if your foundational atoms are poorly chosen or inaccurate, the cascade will amplify that weakness across the entire system.
The specific mathematical detail they use for this is staggering. They calculate what happens if a system's atoms only achieve 50% of their optimal quality.
Right, so let's say you did a really mediocre job designing your base concepts.
Yeah. After just 5 layers of abstraction, the math of the cascade dictates you calculate 0.5 to the power of 5, which means your system only retains about 3% of its potential compression power.
Let that sink in. You lose 97% of your system's capability simply by having a mediocre foundation. This raises an important question about how we build AI today.
Wait, so if a company rushes an AI to market and they build their base concepts by just, I don't know, scraping random unstructured data from the internet.
Which a lot of them do.
Right. And let's say those base concepts are only 50% accurate. The cascade actively punishes them. It will actually multiply their mistakes.
Yes. Finding the natural joints of a domain, the truly accurate load-bearing atoms, is not just some aesthetic design choice for engineers. It is the absolute non-negotiable foundation of scalable intelligence. If you build your AI on arbitrary, fuzzy chunks of text, any logical reasoning built on top of that is going to be incredibly fragile.
Which explains a lot of the AI hallucinations we see today.
Exactly.
The model is trying to compose higher-level logic out of garbage-quality structural primitives. So, okay, the theory is airtight, but we need to know if this actually works inside a machine. Did the second brain researchers manage to build a working version of this without the cascade, blowing up in their faces?
They did. They ran a comprehensive benchmark to test the compression calculus in practice. They took 100 real-world customer service and IT help desk messages.
Okay, so messy, surface-level natural language text?
Very messy.
Like, hey, I ordered a laptop 2 weeks ago and the tracking page is still stuck on pending. Can somebody check the status?
Exactly. They took that unstructured surface text and passed it through a system that converted it into a strict 5-field atomic structure.
And the fields were intent, entity, time, problem, and requested action.
Right. So for that laptop message you just made up, they extract the intent as delivery status check. The entity is laptop order, time is 2 weeks ago, problem is tracking pending, and the action is check shipment status.
So they successfully turned the raw paragraph into a clean, reusable atom.
Yes, and the first metric they checked was the atomic compression ratio, and they achieved a ratio of 1.89.
Meaning they reduced the total number of tokens by 46.2%. They nearly cut the raw data in half.
But compression is useless if it destroys the meaning, right? So they tested for semantic fidelity by feeding those atoms back into a template to see if they could reconstruct the intent of the original message.
How'd it do?
It achieved a 100% fidelity pass rate. Not a single critical piece of information was lost in the compression.
Okay, so the compression numbers are great. But what about retrieval? Because the retrieval metrics they measured were practically flawless too.
They built a retrieval system using these 5 field atoms and pitted it against a standard chunk-based RAG system. The standard system hit 91% recall at 5.
Which means 91% of the time, the correct piece of information was found in the top 5 results.
Right. But the atomic retrieval system hit 100% recall at 5. It achieved perfect retrieval. And while achieving that perfect recall, it required sending 47.5% fewer context tokens to the LLM.
See, that metric alone changes the economics of running an AI. Because the context window, the amount of text you feed an AI to help it answer a question, is highly expensive.
So expensive.
It costs compute power, it adds latency to the response time, and if you stuff it with too much irrelevant fluff, the LLM loses the thread and just gets confused. This atomic system gave the AI perfect accuracy while cutting its required reading material in half.
It conclusively proved that atomic units are a vastly superior intermediate layer for AI memory compared to raw documents.
But I have to ask, if the compression is this clean and the retrieval is perfect, why aren't AI companies already doing this across the board? There has to be a catch when the system tries to actually generate something new with these atoms.
Well, the paper was very transparent about this. The system struggled in one specific area, which they documented as a compositional struggle.
They mean what?
They tested whether the AI could take this library of perfect atoms and autonomously recombine them to solve new, unseen help desk tickets. And the F1 score, which is a standard measure of a model's accuracy, dropped significantly.
Wait, why did it fail to solve new problems if the foundational atoms were flawless?
Because possessing a library of atoms is entirely different from understanding how those atoms are allowed to combine. The system basically attempted to use simple keyword matching to stick atoms together. But keyword matching lacks causality.
Okay, give me an example.
Imagine the AI retrieves 2 atoms, one for refund requested and one for product damaged. Keyword matching just throws them in the same bucket because they share related tags.
But in the real world, the relationship between those two things is what matters. Was the refund requested because the product arrived damaged? Or was the product damaged after the customer initiated the return?
Exactly. The AI lacked the grammar to establish that causal link. As we discussed earlier with mathematics, you need explicit rules. You need a compositional grammar that dictates exactly how atoms can validly connect. A grammar would force the AI to define a temporal or causal edge between product damaged and refund requested before it is allowed to generate a response.
So how do you actually build a compositional grammar? Like, what does that look like in code?
It basically looks like defining the physics of your atomic universe. You aren't just creating objects, you are hard-coding the forces between them. The researchers suggest using directed graphs, where the edges connecting the atoms carry semantic weight.
Okay, so it's not just node A and node B sitting next to each other.
No, it's an explicit rule stating node A causes node B. So, if the AI attempts to connect those atoms with a rule that says node A happens after node B, the grammar rejects the composition because it violates the logic of the domain.
It forces the LLM to arrange the underlying concepts logically before it is allowed to output a single word of English. So we can't just hand an AI a bucket of atoms and expect magic. We have to teach it the physics of how those atoms interact.
Right. And this leads to the paper's conclusion, which is a profound redefinition of what large language models should actually be used for. The industry really needs to stop treating LLMs as massive, static memory banks that are expected to memorize all human knowledge implicitly within their neural weights.
Because asking a neural network to memorize everything is just a highly expensive form of data hoarding. So what does this all mean for the future of AI?
It means we should view LLMs as dynamic fusion engines. Their true, unparalleled capability is navigating, sequencing, and recombining information on the fly. The knowledge itself should not be locked inside the LLM. It should live outside of it, housed in explicit, self-evolving atomic libraries.
Oh, I see.
The LLM acts as the central processor that pulls those atoms in, applies the compositional grammar, and fuses them together to solve complex problems in real time.
So if an LLM is a master chef, right now we are either asking them to plant their own wheat and harvest their own salt, which is forcing them to process raw tokens, or we are handing them a pre-cooked frozen dinner and asking them to microwave it.
Which is document retrieval.
Right. But this framework proves we need to give the chef a pantry of perfectly prepped, highly specific, reusable ingredients and a strict recipe book for how flavors combine.
Yes. And crucially, that pantry needs to self-evolve. As the fusion engine encounters new, recurring patterns in the real world, it should possess the ability to compress those patterns into brand new atoms, continually refining and expanding the structural joints of its own knowledge base.
This completely shifts how we need to think about information, not just for AI, but for ourselves. I mean, when you prep for a major meeting or try to learn a new coding language or even just try to organize a chaotic inbox, you have to stop trying to swallow the encyclopedia, stop hoarding the surface level text.
The goal should always be to identify the structural primitives. Find the reusable atomic units, the underlying chunks that you can actually compose into higher level insights.
Which leaves us with a lingering question to examine as this technology matures. We've established today that human expertise is essentially just compounding layers of compressed atomic units. Look at a chaotic area of your own life or work right now. What is one surface-level mess that you could compress into a reusable, composable atom today to multiply your efficiency tomorrow?
It's a great question to ask yourself.
And if AI systems eventually perfect this compositional grammar and they become capable of compressing and recombining human knowledge far faster and more accurately than our biological brains can, will human language itself eventually become a bottleneck?
It really challenges the very utility of natural language as a tool for complex problem solving, doesn't it?
Definitely. If the AI is operating purely in highly compressed mathematical atoms, we might eventually have to learn the AI's language just to keep up with the speed of its reasoning. Something to keep an eye on as these dynamic fusion engines start coming online. Thank you so much for joining us on this deep dive into the compression layer of intelligence. We hope this framework helps you cut through the noise and start compounding your own knowledge. Until next time, keep exploring, keep questioning, and focus on the atoms.